Hey, let's start. All right. So the big event this week is the test, right? Which is on Wednesday. So I know everyone's aware of that. So I posted the sample test answers. So the sample test answers are posted on the Blackboard page, the same place where the sample test is posted, and so that's there. Don't forget, right, to bring your calculator with you. So some of you did not bring your calculator last time. Bring a calculator with you, right? Okay. And, of course, your survival card. So spend some time making out your survival card between now and Wednesday. And you can use the sample test as a good guide to help you with what needs to go on the sample card, right? So for many of you now, you are kind of teetering on the brink here. You have almost a passing grade or a passing grade, but maybe a low passing grade, so a low C, or maybe you're just below C, okay? And so this test is really going to be important, right? Okay, so that you can get your average up going into the last few weeks of the semester here, so you're not feeling, just panicked about the end of the semester. So you know what you have to do, right? Okay, I think based on the first test, you're well aware of what needs to happen between now and Wednesday at 11:30. Okay, you've got to work on that sample test in the Math Center if you need to, North 925, and you got to make out your survival card, right? So that's will be helpful to you on the test. And then you've also got some homework to finish, all right? And this homework also is very helpful for the test. So there's a homework due tonight. Not many people had worked on that, so there's a homework due tonight. And then there's actually another quiz that's just based on that homework, so it's going to be very similar problems. I moved that back to, it was originally due tonight. I moved that back to Wednesday at the time of the test. Right, so you'll have that done by the time of the test. So there's plenty to do between now and Wednesday. You've got time to do it, but you're not going to be able to lollygag, right? You're going to have to get with it, depending on how far along you are in your preparations, so that by Wednesday at 11:30, right, you'll be well prepared. The time to start is not going to be Wednesday morning, though. Okay, you need to start right now, right? And continue through Wednesday morning so that you can do well on this test, okay? So I know you got other things to do and other things you want to do, right? Okay? But there's not going to be anything more important than doing well on that test on Wednesday of the things you have to do, okay? So you're just going to have to devote the time to it, okay? And you know that, right? I'm preaching to the choir here. You know what's required. The only question is whether you're going to really do that or not, okay? But all of you can do it, all right? I have confidence in everyone's ability to do well on that test, okay? So don't make me look silly, right, okay, by saying that, okay? I want you to do well on that exam. This homework is, you can cover your mouth when you're yawning and things like that, okay? That's kind of like standard courtesy etiquette, right? Okay, so please do that for me. This homework, right? Okay, will be not due on Wednesday. All right, so I'll have to put that back a little bit because the test only runs through 2.4, right? Okay, so so we'll push this one back. Okay. Gio, I'd like to see you after class, okay? Yeah. All right. So that's where we are in terms of preparing for the test, okay? All right. Now, the sample test answers are posted. We're going to look at just a few problems from the sample test today during the lecture period. So we're going to do a little bit of it, but not nearly all of it, not even half of it, okay, just selected problems, the ones that I think, based on the problems that you're missing on the homeworks, and just from my past experience with problems that people miss, a few of the more challenging ones we're going to look at in the after the lecture today, okay? But we can't do the whole sample test in class. You have to do that, most of that on your own, right? And I hope you started on it, so you'll know what's involved, right? It's kind of lengthy, but but not really. Okay, when you get into it, a lot of the problems are don't take that long to complete, but there are several of them. Okay. Do y'all have questions that you want to ask about anything, including what's coming up on the test on Wednesday? Yeah, Arthur. Yeah, you can really tell from the sample test, but it really ends right there. So quadratic functions that we just started talking about last time, that's not on there. Okay, right. So that's why I'm delaying that homework a little bit. So it's very much about linear functions, lots of linear functions, and then sort of, kind of related topics, solving linear equations, solving linear inequalities. No, you can use the point slope formula, or you can use the slope intercept formula. Yeah. Really, either one of those, it's up to you. Okay, yeah. Now, yeah. So what I put on the solutions, how I solved the problem on the solution sheet is not, necessarily the required way. Okay, you can take different steps, but however, right? Make sure you're the one taking the steps, right? So the one thing you cannot do is rely on the calculator to, solve problems for you. Of course, you may need the calculator to help you do computations, right? But that's about as far as it should go. Okay. In terms of the calculator. But otherwise, I wouldn't, unless I don't think there's the instruction, do it this way, but if that's on there, then you would have to follow that instruction. But otherwise, whatever steps you want to take. Okay. And as usual, right, like on that first test, you got to make sure to, if it does require, not every question requires some work. There are some of them are just kind of, questions that can be easily answered. But if it does require some work, then you got to make sure that you show some work, right? Okay, you can't just write down the answer, because I'll get suspicious about where the answer came from. Okay. All right. Other questions like that? So be sure you bring your calculator, right? Let's not have that calculator issue from last time. And make sure you've made out your survival card, okay? That will be really useful to you, okay? All right. All right, so I'm going to talk a little bit about quadratic functions here first, because we're in the middle of quadratic functions, and then we'll get to the to going over the sample test. Don't forget now to finish these homeworks, though, okay? So don't let those get, don't let yourself forget about those. But then the sample test also, you cannot forget about that, okay? That's really important, I think, in preparing for really useful in preparing for the test, okay? So got to do them both, all right? All right. All right, so let's continue. And last time we were looking at some, or we had started, but we really hadn't gotten far into it. Looking at some applications of quadratic functions, because they have lots of applications. So I wanted to show you a few of them that you may encounter elsewhere, perhaps. Okay, in your other classes. This is a famous one because it's a quadratic function that governs the motion of falling bodies. Okay, bodies that are under the the effects of the Earth's gravity. Okay, well actually any gravity field, but in particular the Earth, right? The gravity from the Earth, and this is known from Galileo. Okay, so this is a very old fact in physics. All right, so here's an example of a falling object. So a baseball is popped up, okay, straight up, all right, and then it's going to, of course, eventually come back down, right, with this initial velocity of 80 feet per second, and then the height of the ball is given by this notice that's a quadratic function, so that's a parabola. And you can tell that from the fact that you've got this t squared term, right, in the formula, okay? You can kind of tell where key information from this example comes into the formula. That initial velocity, notice, is going to be the coefficient here of t in this formula. And then this 3 is the initial height of the ball, okay? That's not kind of clear from the statement, but that's the initial height, right? If the ball's being popped up, it's not popped up from ground level, it's popped up from some initial height, then in this case that's 3 feet, okay? Which sounds sort of fair, right? If the ball is being popped up. Now, the minus 16, that constant, that coefficient, that's the leading coefficient of this quadratic function. That minus 16 is related to just the force of the Earth's gravity, okay? So that same coefficient, the minus 16, that's going to apply to any object, okay, that is going up, vertically up and coming straight back down, okay, under the influence of the Earth's gravity, okay. Notice I said any object, all right, any object whatsoever, so it doesn't necessarily have to just be a baseball, okay. And that was Galileo's famous discovery, okay, that all objects, okay, no matter how large or small, they're going to behave exactly the same under the influence of the Earth's gravity if you ignore aerodynamics, okay? So wind resistance will have an effect, but if you have objects that are not very aerodynamic, they're going to fall at the same rate, okay? And so, see, that happened right there, right, okay? Those objects are going to fall at the same rate. So it's the same formula that applies to any object if we ignore wind resistance, okay? It's the same formula that applies to any object, and it doesn't matter what the weight of the object is. So notice that the weight of the object is not involved in that formula at all, okay, right? What's in that formula is, again, this coefficient, which has to do with just the strengths of the Earth's gravity, okay? That coefficient would be different on maybe different planets, all right, where the gravitational field is different. And then here, this is just the initial velocity of the object, right, okay? The initial upward velocity of the object, and that's the initial height of the object. But the weight of the object makes no difference, okay? And Galileo got into a lot of trouble for that discovery. Seems funny right now, okay? But Galileo got into trouble for that because that contradicted the teachings of the Catholic Church, all right, which were based on the beliefs of Aristotle, and Aristotle thought objects with different weight fell at different rates, okay, but they do not, okay, and so that's what Galileo stated, and for other reasons too, that's got Galileo in trouble with the Catholic Church. All right, so anyway, let's see if we can answer some questions now that we recognize that that is a quadratic function, okay? And we know the basic properties of quadratic functions, and so I think we can use those to answer these questions. This one's pretty easy, though. You really don't need to know that much about quadratic functions to answer this question, right? It just says, what's the height of the ball after 2 seconds? So that's really just a function question. We could have answered that right at the beginning of the class, right? All we have to do to answer this question, right, is just to plug 2 into the formula, correct? Okay, so in other words there, we just have to calculate h of 2. Let's see what that turns out to be. I think we can do that pretty easily there. So we have minus 16 times 2 squared plus 80 times 2, right, plus 3. So that's minus 16 times 4 plus 160, I think, right, plus 3. So let's see, minus 16 times 4, what is that, minus 64? I think so, plus 160, and then plus 3, right? So that looks like, is that 99? I think so, okay. if I did my arithmetic right there. So the height of the ball after 2 seconds, that's going to be 99 feet, okay? Because the height here is measured in feet, I think, all right? That's not entirely clear, but I think because this this initial velocity is given in feet per second, then our height is being measured in feet, right? So after 2 seconds, the ball is, at height 99 feet. We don't really know if at that point, so far, right, we don't really know if the ball is still going up, correct, or if the ball is at that time coming back down, all right? We just know its height is 99 feet, okay? All right, so again, no particular knowledge of quadratic functions necessary to answer that question, but now here's where things get more interesting, okay? This is a very natural question to ask, right? What would be the maximum height of the ball, all right? So how high is that ball going to get? Maybe it's 99 feet, okay? Maybe it's at its maximum height after 2 seconds. But let's see how we can answer that question. And see, this is where our knowledge of quadratic functions is really going to be helpful to us, okay? It would be nice if we had a graph of that function, because we could just look at the graph, and from the graph we would be able to get at least an estimate for what the maximum height of that ball is, okay? So we could draw a graph using either our calculator, or we could draw a graph using the computer, and I'm going to use Desmos here in a second, and we'll actually look at a nice graph of this function. But because of our knowledge of quadratic functions, we can imagine what this graph is going to look like, Ben, without actually having to draw it precisely, okay? All right? Because we know enough about quadratic functions to already have an idea of what this graph is going to look like, okay? So, Ben, what can you tell me about that graph when you graph the minus 16t squared plus the 80t plus the 3? What's that picture going to look like, okay? And we can maybe make a rough sketch of that. So what sort of curve are you going to get when you graph that formula? Well, just in general, what type of curve does quadratic functions give us? Do you remember the name of those curves? Somebody help him out here. What's it called? Parabola, right? That's a parabola. Okay, so that's an important thing to remember, all right? So you're going to get a parabola, and a parabola is just that U-shaped curve, right? Okay, so we're going to get this U-shaped curve. All right, Ben, so all right, so let's go a little bit further into that. Which way is that parabola opening, okay? Is it opening up, or is it opening down? So it's going to be U-shaped, right? So it could be a bowl shape like this. That's what I call opening up. Or it could be kind of a hill-shaped, right, like this, right? That's what I call opening down. So which way is that going? Is it pointing up, or is it pointing down? Pointing down, right. Why do you know that? Because of the minus 16, yeah, right, okay? So that's really important, right? That leading coefficient is negative, so that means this parabola is opening downward. Well, now we've mentioned that, let's go ahead and write down what the coefficients are. So our leading coefficient is minus 16, right? That's what that number is called, the leading coefficient. What's the middle coefficient? That's pretty easy. What? 80, right? And then the constant coefficient that we usually label C, that's 3, okay? So you're right, Ben, that a parabola, and I'm going to draw a really ugly rough sketch of it here, okay? There's the t-axis, that's elapsed time. Here's the height axis, all right? So that parabola is indeed opening down, okay? Like this, all right? What's this number right there? We know this also now. 3, right. Arthur, why do you know that's 3? That's the y-intercept, right, okay? So, and that has to be 3, right? Remember, the y-intercept is always the same as your constant coefficient. That just tells you the initial height of the ball, right? When time is 0, right, okay, the ball is, that is right when it leaves the bat, right? At time 0, the ball is at height 3 feet, okay? I should cut my graph off a little bit here. I sort of drew the whole parabola, right? But some of this parabola really isn't part of the graph in this situation because, remember, this formula is telling me about the height of the baseball, right? So the height of the baseball is not going to go negative. So you don't have to draw this part of the parabola over here or over here, right? Because the elapsed time cannot be negative either. So the domain of this particular quadratic function is restricted a little bit, right? Okay. You're not going to have elapsed time less than 0, and the height of the parabola is not going to come down here to negative, right? So this parabola should get cut off right there, okay? All right, now, so there's just a really ugly, rough sketch, right? Okay, and we're looking for where the height of the ball is maximum. So where is that on the parabola? Where's h the highest here? Yeah, right up there, right, at that tip, right? And that's called the vertex. So so we can answer this question, right, by figuring out where that vertex, right, is located. But we know how to do that, right, because we have a formula for the vertex. Let's recall what that formula is, right? The only thing you really need to remember about that formula is the first coordinate of the vertex, the x-coordinate of the vertex, or in this case, the t-coordinate of the vertex. Remember, that's always minus b over 2a, okay? And then you get the y-coordinate, or in this case, the h-coordinate, by just taking that number, the minus b over 2a, right, and plugging it into your formula. Well, we already figured out what b and a are, right? So we can just plug those in there. So I get minus 80 over 2 times a minus 16, and that works out to be minus 80 over minus 32. What does that reduce to? What now? 2.5? Okay, excellent. All right, so 2.5. So apparently that, this is 2.5 right here, so that means that baseball reaches its maximum height right after 2.5 seconds. So after 2 seconds, it was still going up, right? When it was at 99 feet, it was still going up because it's going to reach its maximum height after 2.5 seconds. And then going to start dropping back off again, right? Okay, until it ultimately there hits the ground. And then you can just calculate the maximum height by plugging the 2.5 into your formula. So you have to do a little bit of arithmetic there. So we have minus 16 times 2.5 squared plus 80 times 2.5, and then plus that extra 3 there. What is that going to work out to be now? So somebody do those calculations for me. So it's going to be a little bit more than 99, okay? What now? 103, okay? So if you grind through those computations, Arthur says that comes out to be 103. So right there at, if that's correct, right there at 103, right, that's going to be the maximum height. So there's our answer. Okay. So an important formula from physics there, right? Oh, I want to point out that this graph is not the path of the ball. Okay, so sometimes students get confused and think that ball is traveling up at an angle, but it's not. The baseball is going straight up and coming straight back down. Okay, so it's not traveling along this path. Okay, but that graph does tell you the height, right? Okay, of the baseball after a given number of seconds. So that's just a vertex question. Now, the other thing we might want to know there is When does the ball hit the ground again? Okay, so it's going to hit the ground right here, right? Okay, because that is when the height is 0, correct? When it hits the ground. So right at that point, that's when the height is 0. Of course, what is that point called on your graph? What's the geometric name for that point? What? That's x-intercept. Sure, right. Okay, that is the x-intercept. So this question, this last question, when does the ball hit the ground? That's just a question about x-intercepts. Okay, so really, actually, we didn't need to know much about quadratic functions to answer that last question either, because functions in general, right, have x-intercepts. And how do you find the x-intercepts? Yeah, set y equal to 0. Okay, y'all got to help Arthur answering the questions here, all right, today, because y'all going to need to know this as well, right? So you set y equal to 0, right? Okay, so in your formula, right, there's the formula. Just set y to 0, and then see if you can solve that equation. This looks like maybe that's a fun equation to solve here. So we have minus 16t squared plus 80t, right? Okay, plus 3. That's equal to 0. Okay. Wow. Any suggestions on there on how we can go about solving that equation? Yeah, I could move the 3 over to the left-hand side, okay? But in this case, Arthur, that's not going to help me, all right? This is not a linear equation, all right? So this equation is going to be more challenging to solve than the equations in Chapter 2, the equations that you're going to have on the test, okay? And what makes it challenging is the fact that you've got that unknown squared, okay, all right, in the equation. So do we know any general techniques for solving equations like this? What can we try, Nadine? Could we do what now? Yeah, one thing we might do here is try factoring, okay? So we might try factoring there the right-hand side, okay, and see if we can factor that, okay? Not an easy thing to think about factoring, though, is it? Okay, that one seems pretty tough to. That one seems pretty tough there to factor. What if that doesn't factor, or what if we're not able to factor that? Maybe it will factor and we just cannot see the factoring. Any other suggestions for what we might be able to do? So what if you get stumped on factoring it? Do y'all know any alternative ways of solving an equation like this? Well, all right, so this is something that we have to work on, right? Okay. How can we find x-intercepts of a quadratic function, or how can we solve an equation like this where the unknown is squared? So Nadine, your idea is very valid, okay? So one thing we might try doing is factoring, all right? And but if we are not able to factor, or maybe the expression just doesn't factor, okay, then what would be our alternatives to that, okay? So what else could we try if the factoring is not going to pay off for us, okay? So so that's something that we need to think about, right? That we have to work on and explore. How are we going to solve this equation to find the x-intercepts? Let's convince ourselves that there even is an x-intercept, though, okay? Because not all equations have x-intercepts, but I think it must have an x-intercept, right? Because we know the graph looks like this, correct? And we know what the vertex is. You know the vertex is here at 2.5 and 103, right? So the vertex is above the x-axis, and since the parabola opens down, I think it's just got to cross the x-axis somewhere, right? So that equation does have to have some solutions. It's got to have some solutions. There has to be some x-intercepts. We can tell that just geometrically from the picture. So let's take a look at the graph here, because I've got this one graphed, and see what we can see from the graph, okay? All right, so there's the graph. Wow, we did a pretty good rough sketch of that graph, okay? See, that's what that knowledge of parabolas can, properties of parabolas can help you with, okay? We made a decent graph of that one already just by hand, and but on this more accurate graph that I graphed with Desmos here, we get a much better idea of what that x-intercept is, right? Okay, what does it look like it is? Really, they're darn close to, yeah, darn close to 5, right? Okay, but not quite, all right? And notice there's another x-intercept right here, just a little bit less than 0, okay? So, but this is the one that we're really interested in, okay, is that x-intercept right there, all right? So what would that, how are we going to figure out what that x-intercept is? How can we solve that equation to find that x-intercept? All right. Well, let's put that let's put that problem not aside, okay? But let's think about that's something that we have to work on, right? Is how can we find x-intercepts for quadratic functions? But we know how to find the vertex, right? Okay. So that we were able to answer there completely. Let's take a look at another example. Kind of very similar here, all right, but just in a different context, okay? So here's for people who are going to major in business, all right? This is a kind of a business application of quadratic functions that you may see in, I don't know, your economics class, all right? All right, so Benny sells sandals at a souvenir shop near the beach, okay, and Benny knows from past data that the monthly profit, okay, from the sale of the sandals is given by this formula, okay, and X here is the monthly demand. Monthly demand is the number of sandals that he sells, all right? So obviously, right, the number of sandals that he sells controls what his profit is going to be. In other words, the profit is a function of the demand, the sales, okay? So that makes perfectly good logical sense, right? And here's the formula now that actually determines, right, the profit based on the demand, okay? And notice again, that is a quadratic function again, right? Okay? Because here we have the unknown squared in the formula, all right? Okay, so that first question is exactly sort of a question you would ask Benny, all right? What is the maximum profit, okay? So what is the maximum profit Benny's going to be able to earn, right, from the sale of these sandals, maximum monthly profit, and what demand would lead to that maximum profit, okay? Now, initially, you might think, if you're just thinking naively here, you might think, there is no maximum profit, okay? The more Benny sells, the more profit he's going to make, right? Okay? And so again, if you're just thinking naively, that kind of makes sense, all right? But you have to think more carefully about profit and demand to see that indeed that's not the case, okay? That probably won't be the case. Given that we know that this formula gives us the profit, we can immediately see that there's a maximum profit. Because again, what sort of function is that? Yeah, that's quadratic, right? So when we graph it, we're going to get what sort of picture, of course? What? Downward facing what? Parabola, right, okay? So you're going to get a parabola that opens downward, and we know that from the coefficients, correct? So we can tell that from the coefficients. All right, let's see. So what are those coefficients? That's pretty easy. What's the leading coefficient? Be careful here now. Yeah, -3, right? It's not 12, okay? Even though I wrote the 12 first, I did that for convenience because this is a minus sign, okay? But the leading coefficient is -3, all right? That's the coefficient of the x squared. What's the middle coefficient, although it's not in the middle here? 12, right, okay? And then the constant coefficient there is -9, all right? So we know when we graph this, right, if we make a really rough sketch, that parabola, right, is going to open downward, okay? And so it's going to look something like this, right? And what's this point right here? Yeah, that's -9, right, okay? That's the y-intercept. We can have a negative y-intercept here, all right? In this case, we can have a negative y-intercept. Why? Because what's that y-intercept telling us? In this situation about Benny's profit here. He's losing money, that's right, okay? So you can have negative profit, all right? So you can have negative profit if Benny's losing money. And so if Benny doesn't sell any sandals for some reason in a given month, maybe bad weather or something, Benny doesn't sell any sandals, he's going to be losing 900, right, on the sandals, okay? So that's possible, all right? And in the picture there, of course, where is Benny's profit maximized? At the vertex, sure, right, okay? So just like before, we know the profit's going to be highest here, right? Okay, right at that vertex. So let's see what that vertex is going to be, and that will completely answer this question, right? So we just have to use our vertex formula. But we just have to remember the vertex formula, right? Because we've got all of the coefficients. So we're going to have minus b, which is -12. Be careful to get the signs right. Over 2 times a -3. So that turns out to be -12 over -6, which is, oh, that's easy, okay, 2, right? So this value, the x-coordinate of the vertex, right, is going to be 2. So it tells us that Benny profit's going to be highest if he sells 200 sandals or 200 pairs of sandals, right, in a month. Okay. And let's see, what is that maximum profit? That's easy to compute, right? All we have to do is plug the 2 right into our formula. So we get 12 times 2 minus 3 times 2 squared minus 9. So that's going to be 24 minus 12 minus 9. So 3, right? So my graph is drawn very well to scale, but it's drawn good enough, right, that we can answer these questions. Looks like the maximum monthly profit on the sale of the sandals is 300, right, if the demand is 200, okay? Now, why isn't it the case, all right, that, why is it not the case that the more we sell, that the demand goes up? Why doesn't the profit just keep going up? So why isn't this just an increasing function? Why does it switch from increasing to decreasing? Okay, why would the profit go down if your demand continues to go up? Why doesn't the profit continue to go up? Okay, well, you have to think about how demand for items works, right? Okay, how can you increase the demand for an item? By having less what? By lowering the price. Okay, right. Okay. Yeah, all right. See, demand, especially for things like sandals, is very sensitive to price. Okay. Some items are not completely sensitive to price, like, for instance, gasoline, because people have to buy gasoline and still have to drive to work, right, in various places. Okay. So if you increase the price of gasoline, demand will go down, but not substantially. But for things like sandals, right, which are just discretionary items, you increase the price too much, right, and the demand is going to go down, right? So apparently what has happened here is, to get that demand up, right, to make the demand increase, Benny has had to lower the price. Okay, that makes the demand increase. Well, okay, apparently, though, he's had to lower the price so much that his profit has gone down. Okay, so that's how you can have larger demand but lower profit. Okay, lower the price to increase the demand, but that will also lower profit. Okay, so apparently that's what happens. That's what's happened here in this, or what happens here in this particular situation. Now, another thing Benny would be interested in is, because he doesn't want to lose money, right? So another thing Benny would be interested in is, what are the break-even points here? When is the profit not negative, but not necessarily positive? Okay, so when is he not losing money, all right? How many will he have to sell to not lose money here, right? So that's going to correspond to the x-intercepts, correct? Okay, because right at the x-intercepts, the profit is going to be 0. Okay, so that's not an ideal situation. He's not making money, but at least he's not losing money, right? Okay, so so we can find Benny's break-even points by finding the x-intercepts. But you guys already told me how to do that, right? Okay, just take that formula and set it equal to 0. Let's see if we have any more luck now with this equation than we did with the one before. Okay, so here now we have again this equation to solve that involves having the unknown squared. Okay. All right, so Nadine, you suggested one thing we might try here is factoring, okay? Because that is a good initial technique to try with solving equations where the unknown is squared, okay? But if the factoring turns out to be intractable for some reason, we just can't carry it out, we're still kind of stuck with what we're going to do next, right? Let's see if we can factor this one, though. Maybe we'll have better luck with this one. So, Nadine, if you're starting to factor that, what would you factor first? What?
Well, okay, so I still use the method that we learned, like, way back.
Mm-hmm.
So I just multiply 12 and 9, and I do the little x, and then the negative 3 goes on the bottom, and basically it just has to multiply to 96 and add up to... Wait, I don't know if I'm confused.
Okay. Oh, well, all right. So let me make this easier for you, okay? Let me make the techniques easier for you. What I would start with, and sometimes you can do this and sometimes you can't, is just look at the coefficients, Nadine, and see if there's a number, don't worry about the variables, just see if there's a number you can factor from the coefficients, okay? See if there's something you can factor from the coefficients, all right? And then we'll worry about the unknowns in a second, all right? So is there some number you can factor from 12, 3, and 9, in other words? 3, right, okay? So factor that out first, all right? Because then that will make all your coefficients smaller. Now, I'm actually going to factor out, instead of just positive 3, I'm going to factor out negative 3. And the reason I'm doing that is because if I factor out minus 3, this coefficient will end up being positive 1. And that also makes my factoring life easier, okay? So I'm going to factor out first here negative 3, okay? That's still factoring. So let's see, when I factor minus 3 from minus 3x squared, that leaves me with x squared. I'm going to write that first. And then when you factor minus 3 from 12, that leaves you with minus 4x. So I'm going to write that second. And then when you factor minus 3 from positive 9 there, what does that leave you with? Did I write it down right here? Oh, that was supposed to be a negative 9, right? Okay. All right. All right, so that's better. All right. So we get minus 3 times, and then in parentheses, x squared minus 4x plus 3. And now you're going to try to factor the x squared minus 4x plus 3. But see, that's much easier to factor, right, Nadine? You can do that one pretty quickly. How does that factor now? So see, I'm going to break that up into 2 parentheses. How does that factor? X squared minus 4x plus 3. It's got to have x and x, right, to get the x squared? And what about to get the 3? Only one way to write 3 as a product. How do you write 3 as a product? 1 and 3, right? Okay. That's a prime number, so you have to write it as 1 times itself. And then what about the signs? They're both negative, right? Okay. So you will get in the middle, x times minus 3 is minus 3x, and then minus 1 times x is minus x. So you'll have minus 3x minus x is minus 4x. So that is the correct factorization, okay? So you have this product equals 0, and that means one of 3 things has to be the case, because you've got 3 factors multiplied together to give you 0. So that means either minus 3 is 0, but that can't be, because minus 3 is just not 0, right? Or x minus 1 could be 0, or x minus 3 could be 0. And there are the 2 solutions. Yay! There are the 2 break-even points for Benny's sandals here. One of them is at 1, and one of them is at 3. So if Benny sells 100 pairs in a month, he's going to break even. And if he sells 300 pairs in a month, he's also, ironically, going to break even. Okay? He will have no profit if he sells 300. That's because he has to lower the price sufficiently to raise the demand to 300. So that eats up his profit. His maximum profit will be at when he sells 200. Okay? Cool, right? So that's a classic business question, all right? And there we answered it just from our knowledge of, in this case, quadratic functions, okay? All right, so we still have a couple more applications that we want to look at, but I want to show you now something that you're already familiar with, okay? So this will be not news to most of you. But here's the answer to the question that we were thinking about a moment ago. If we've got a quadratic equation, so this is called a quadratic equation. Notice that's a quadratic function, ax squared plus bx plus c, set equal to 0. So quadratic equations result when you are, or one way they result, is when you are trying to find x-intercepts for quadratic functions, okay? And so one way to try to solve this equation is by factoring. So we were able to do that with Benny's equation, right? Benny's profit equation. But if you cannot factor, then there's this famous formula that's known for also deriving the solutions to a quadratic equation, and it's called, appropriately, the quadratic formula, okay? So this is the formula you can use to just by plugging in coefficients from your quadratic equation to solve and find solutions to a quadratic equation. All right, so notice quadratic equation, right, is the one side of the equation is a quadratic function that has been set equal to 0. So this formula only applies to equations that have this format. So don't try to apply this to, just any equation, right, okay? It only works for quadratic equations, typically that's going to be an equation where the unknown is squared. All right, so when you encounter an equation where the unknown is squared 99% of the time, that will be a quadratic equation, and so you likely can solve it either by factoring or by using the so-called quadratic formula, okay? And to use the quadratic formula, all you have to do is to recognize what the leading and middle and constant coefficient are, right? Okay, plug them into your formula and simplify. Sometimes that's kind of challenging, but plug them into the formula and simplify, do the arithmetic and simplify, and you can arrive at your solutions to your quadratic equation, okay? Or sometimes quadratic equations don't have solutions, and you'll also be able to tell from the quadratic formula whether solutions exist or not. I should be careful here whether real number solutions exist or not, okay? Because we're getting ready to talk about solutions to quadratic equations that are not real numbers. We're going to talk about types of numbers that don't exist on the real number line, okay, but are still useful numbers. Okay, all right, so there's the formula. Let's just apply it at least once here, okay? So let's see if we can find the x-intercepts of this quadratic function. Okay, so that's pretty standard quadratic function, right? Doesn't look like anything unusual. The leading coefficient here is 2, and the constant coefficient there is -4. I'm sorry, the middle coefficient is -4, and the constant coefficient there is -1. Be sure you include the sign, right, with your coefficient. So don't write that as +4 or +1. Otherwise, you'll make sign mistakes. All right, so again, to find the x-intercepts, right, you're going to take your formula and set it to 0, and notice that results in a quadratic equation, right? You have an equation there where the unknown is squared. So we might be able to solve this by factoring, but I don't think that expression, unfortunately, is going to factor. So factoring is not going to get us very far in trying to solve this equation. But I do recommend when you're solving quadratic equations, try to factor first, okay? Try to factor first, because usually that's the fastest and less error-prone method for solving the equation, okay? But if you cannot figure out how to factor, you can always use the formula. The formula always applies. By the way, this formula has been known since antiquity, so this is one of the oldest mathematical formulas, that was ever written down, okay? So you can find bits and pieces of this formula in sort of different formats from very, very ancient texts, okay? So it was probably known before recorded history. Before people even started writing, they probably knew how to solve quadratic equations using that formula, okay? So that tells you how useful it is, right? Okay. All right, so I don't think factoring is going to get us very far, so let's try writing down the solutions with the formula. All right, so be careful about the signs. That's really the only real error-prone part of using the quadratic formula. So you have minus b, but b itself is -4, right? And then notice in the formula it says plus or minus. Of course, that's not a new arithmetic operation, plus minus. That just means you might have two solutions to your equation. You know, one you get by adding this radical to the -4, and then another you get by subtracting this radical from the -4, okay? So quadratic equations can have two solutions because parabolas can have two x-intercepts, but they don't have to have any x-intercepts. So just because you write down a quadratic equation doesn't mean it's going to have a real number solution. Let's see now. So b squared, so that's -4 squared. -4 times a is 2. And c is -1. All of this over 2 times a, right? So 2 times 2. And, well, there they are, okay? There are the two solutions to that quadratic equation, okay? But now we need to simplify this sum, right? So we need to carry out as much of this arithmetic as we can by hand. So minus a minus 4 is plus 4, plus or minus the square root of negative 4 squared is positive 16. Okay, here's where students like to make mistakes, all right, is with this second term right here, and it's the sign. So you have to watch your signs really careful on this term. All right, so let's see what this product is. Minus 4 times 2 is negative 8, right? But negative 8 times minus 1 is positive 8, okay? So right under that radical, put plus 8 here, okay? Plus 8. So I get more mistakes from students with the sign of this term than almost any other aspect of the quadratic formula. All over 4. All right, so far it seems pretty good, right? So we have 4 plus or minus the square root of 24 over 4. Now, unfortunately, 24 is not a perfect square, okay? 24 is not a perfect square, so you're not going to be able to completely simplify the square root, okay? If that were square root of 25, you could write down 5, correct? But 24 is not a perfect square, so that square root is going to end up in your answer. If you only need a decimal approximation for your x-intercepts here, then you can go ahead and use your calculator at this point and get a decimal approximation, okay? So use your calculator to get an approximate value for square root of 24, okay? You know, add or subtract that from 4 and divide by 4, and you can get a decimal approximation for these two x-intercepts. Let's see what that would be. So we would have approximately 4 plus or minus, and what's the square root of 24 to a couple of decimal places at least? What, 4.89? Okay. And then divided by 4, don't forget. So that's going to be one solution is going to be 8.89 divided by 4. That's one solution, right? Okay. But the other solution then is minus 0.89 divided by 4. All right? Because remember, you have to add and subtract. So 4 plus 4, 8.89 divided by 4. And then 4 minus 4.89, that's minus 0.89 divided by 4. What are those approximately, Arthur? Minus 0.2 something. What? Negative 0.22, okay, and this one is 2.22. All right, okay, so there we have decimal approximations for the two x-intercepts. All right, now, however, if you need to write down the exact value of the x-intercepts, not a decimal approximation, that's what these two numbers are. Let me show you how to simplify this a little further by hand, okay? So we can keep simplifying this. We can't completely simplify it, but we can simplify this a little bit more by hand by trying to simplify square root of 24. So what you need to do is write that 24 as a product of a perfect square times another number. So can you write 24 as a perfect square times another number? There are lots of ways of writing 24 as a product. You could write it as 2 times 12, but see, that's not helpful because neither 2 nor 12 is a perfect square. You could also write it as 3 times 8, but again, that's not helpful. What's another way we can write it as a product? 24. Right now? Yeah, 4 times 6. And that's what you want to do because 4 is a perfect square, okay? So you can extract square root of 4. So you have 4 plus or minus 2 times the square root of 6 over 4. All right, that's a little bit better, okay? But now I'm going to go one step further, because out of the 4 and the 2, not from the 6 is trapped under the radical, so you have to leave that. But from the 4 and the 2, you can factor out a 2 in the top. So that would give you 2 times 2 plus or minus the square root of 6 over 4. And the reason I did that is because 2 divides into 4 twice. So we end up here with 2 plus or minus the square root of 6 over 2. That's completely simplified by hand. All right, so I don't think I can simplify that any further without getting a decimal approximation on the calculator. All right. So your two solutions would be 2 plus the square root of 6 over 2, which I think is approximately 2.22, and then the other one would be 2 minus the square root of 6 over 2, which is apparently about minus 0.22. Okay. So that's simplified by hand. But those are the exact solutions, okay? Not decimal approximations, but the exact solutions, all right, to that quadratic equation. Okay, well, there's our first example. We got to solve a few more, but there's our first example with using the quadratic formula. So I know you've seen the quadratic formula before, but we're going to exploit it a lot, okay? Mainly to help us find x-intercepts for quadratic functions, okay? All right, let's quit right there with the lecture. All right, and then we're going to look at some of the problems now from the sample test. So if you got the sample test, you can pull it out, okay? But I'm going to project it, all right? And then we're going to look at just some of the key problems, I think, from that sample test to get you started thinking about the sample test, all right? Okay, so let's take a few minutes, though, before we dive into that, all right? So let's stop there, and we'll come back maybe at about 12:40 and work some of those sample test problems, okay? Okay, let's resume. One thing that I forgot to mention earlier, if I mentioned it, I forgot that I mentioned it, so let me mention it again. Today is the, it's usually around this time of the semester, but it varies slightly each semester. But today is the last day to drop with a W, okay? So if you are thinking, oh, I'm not going to be able to do well on test number 2, there's just no way, I don't have time to prepare for it, or I'm not really into preparing for it, and you know my grade so far is not that great, then you should seriously consider dropping, all right? So you don't get a bad grade on your as your final grade. After today, you will get a letter grade. This is for all your classes. So you will get a letter grade, okay? And there's nothing I can do about that. You'll get a letter grade. And so, so if you're thinking, I'm not going to survive for whatever reason, then now is the time to act, all right? So you can go talk to your advisor, or I'm not sure you need me to talk to your advisor. You can just go to the registrar's office or you can do this online. Just drop the class, okay, so that you don't end up getting a grade that affects your GPA, all right? A W is what you'll get. That will not affect your GPA, okay? But a letter grade, of course, is going to get factored into your GPA. Of course, if it's a good letter grade, that's good, right? But if you're thinking it's not going to be a good letter grade, then you need to make some decisions there, right? Either I want to drop, or wow, I've really got to make sure that I prepare well for the test on Wednesday, right? So I don't put myself in this bad situation, okay? So I just want to remind you of that. That's true of all your classes, not just this one, okay? So if you're struggling in any of your other classes, be thinking about, right, what you want to do, okay? All right. So I want to go through some of these problems, but but we want to go through this very quickly. So I'm just going to show you a problem, and we're just going to take a few minutes. But of course, you can discuss it with your friends on each problem. But if you don't get the complete solution to the problem in the short amount of time that we've got, so we're only going to take like 3 or 4 minutes a problem. All you have to do is think about what your strategy is going to be. So just what the initial steps would be to solve that problem, right? Okay, and so just, where would I start here on this problem, right? What are the first things that I would do? And then if you don't get completely finished, that's fine. Because all of the solutions, again, to the sample test are posted, but I don't want you looking at the solutions while we're doing this, okay? Because that will not be helpful, all right, okay? Because I want you to think about each problem, okay, right? And how you would approach it on the test, all right? And so that's why we're going to go kind of quickly, because on the test, right, you're also going to have to go kind of rapidly, right? Okay, so so that's our goal. And then so after a few minutes, 3 or 4 minutes with each problem, well, some of them are short, but after a few minutes with each problem, we'll stop, and then I'll have someone just say to the class, here's what I did first, right? And so even if you didn't come up with the whole solution, which for some of these are kind of lengthy, so it's unlikely you'll get the whole problem done in just the short amount of time. Just how you would start that, right? Okay, and then if you're stumped there, then maybe the class can help you, right, with what the first steps would be. And because you've got, again, we have the whole solutions, right? So you can. After you've worked through the sample test, right, you're going to look at the answers that are posted. So you'll be able to see all of these complete solutions already, right, before we take the test. Okay, so that's our goal here, is just how would we approach this problem, right, when we see it, because we're likely to see it, or something like this, right, on the exam, all right? All right, so let's start with a pretty quick one, though, okay? This is problem number 3, all right? So what this says is we have a laptop computer, right, and it costs $2,000 new, and but it's going to lose value after it's new, right? So it loses $100 in value each month, okay, from its resale value, right? And then we just want to write down a formula for what the resale value would be after T months. So after T elapsed months, how would you calculate there? What's the formula, right, for calculating the resale value of that PC here? Let me see if I can make this a little bit bigger. All right, so that may help some. Okay. All right, so just that problem, right? So just your initial thoughts there, right, on how you would start that, okay? So let's take about 3 minutes for that. This one you might be able to write down the whole solution, but otherwise, just where would you start there, okay? Or what are you thinking when you see that problem, okay? So, and again, you can talk with your friends, right? This is not an individual thing, so talk with your partners there, whoever's next to you, right? Okay, they may have some ideas as well. And then I'm going to ask someone to share what they thought, okay? You can ask me and Taylor too, so... Are we out of time there? Have you already solved that one? That was pretty fast. Okay, let's stop there. Eduardo, what did you think about this one? Speak up there for me. So what? 2,000 minus 100t, right? So you went ahead and solved it there. Why did you? How did you arrive at? What were you thinking about in getting that particular formula? Okay, so why were you thinking it's that instead of something else? The original price is 2,000, right? Oh, so you're losing 100 each month. So that the fact that you're losing 100 each month tells you what? What value does that really sort of indicate to you? It's going down, right? So yeah. So what would that number be called there? The amount that we're losing each month. What do you call that in general? He doesn't know what I'm asking. Y'all know what I'm asking. What is that number? Just in general, what would that number be called? Slope, right? Okay, yeah, all right. So you're thinking the minus 100 will be the slope, right? Because we're losing that much each month, correct? Okay, from our original price of 2,000. Okay, so this would be the y-intercept, right? Because when at the beginning, when t is 0, right, the value there is 2,000. Okay, yeah, that's perfect. See, all right. So that's a nice linear function, right? Okay, we're losing the same amount each month, correct? So that's linear, right? And so we don't really need points here, right, to write down the formula for that linear function because we've got the slope given to us, and this 2,000 happens to be the y-intercept, right? So we can just write down that formula pretty quickly, right? Okay, great. All right, perfect. That's exactly, I think, the way you want to be thinking about that. All right. Now, here's another thing that I want you to be able to do. Make sure you can do this, okay? Because this will make me crazy if you cannot do this, all right? So as soon as I grade this problem, if you miss it, this type of problem, if you miss it, it's going to give me I'm going to have a negative perception of you, all right, for grading the rest of the test, all right? Because graphing a straight line is just so easy, okay, that should just be a gimme problem, all right? And yet, I still have students I think in my Calculus 2 class that could not graph a straight line, okay? So, that's really depressing, all right? But you're going to be able to graph them, all right, correctly. All right, so what about graphing this straight line? We just have y equals 1 minus 6x. What would you do to graph that, okay? So what steps would you take, okay? There's kind of different ways of going about it, but what would you do in order to graph that, okay? So just take a couple of minutes there. You can just scribble something. Don't have to make a beautiful graph. On the test, you may have some graphing paper, so you might be able to make a nice graph on the test. Okay, yeah, I got really quiet, so I think everyone's figured out what they need to do, right? Maybe you're just in the process of doing it, all right? So let's talk about how you would attack that problem. Juliana, what would you do? You would graph the y-intercept first, okay? So that sounds like a good start. So graphing the y-intercept, let's try doing that here. So what is the y-intercept, Juliana? 1. So we got to find 1 on there. That's hard to do on this, the way this is scaled, right? But I think 1 is right there, right? Okay, so we got that point, okay? And then what would you try? To the left 1 and down 6. So I think you said that backwards there, all right? So we know the y-intercept is 1, right? Okay, and the slope there is how much there, Juliana? What? -6, right? Okay, so you said starting from this point, I can get another point by going what direction? I can go either left or right, right? So okay, so yeah, but that's where you have to be careful, right? If I go to the right 1, then I can go down 6, okay? All right, but if I go to the left 1, I'll have to go up 6, okay? Right, so if we go to the right 1, then we can go down 6. That would put me at -5, right? Right there? About right there on this scaling, right? Okay, down 6 from 1 would be -5, and there you've got it, see? All right, you already have 2 points, and if you've thought about those 2 points carefully, then you can connect those with a straight line, right? And there's the graph of your line, right? So that's a great way of doing it, okay? Did somebody have a slightly different technique? Because there's more than one way of generating that line. So we're going to do something different than using the slope and the y-intercept. How else can you plot this line? Yeah, plug in values, right. Okay, so you can generate points on the a line, right, by kind of making out a little table here, right? So pick values for x or y, actually, plug them in, and then find what the other point is, right? What the other variable is in that case. So just plug in values for x, right? Okay. 0, of course, is going to give you 1, right? 1 there would be -5. Those are these 2 points, right? But you could plug in -1 if you wanted to, correct? That's going to give you 7. Okay, for y, just plug in any points that you want there, right? Any values that you want for x, find the matching y value, and then just plot those points, okay? So you can do it just through plotting points without having to figure out what the y-intercept is and what the slope is, correct, for that line. So there's 2 ways, at least there, of getting that one correct, okay? So I think y'all should do that right on a test. Okay. Here's one now that did not go over well on the homework, okay? When you had problems like this one on the homework, this is just solving an equation, okay? We're just solving an equation, and this is actually just a linear equation, because notice that your variable x is only raised to the first power in this equation. So that's not a quadratic equation, thank goodness, right? Okay, that's just a linear equation. So that should be simpler than solving a quadratic equation. All right, so let's see, where would we start with solving that linear equation? The first step here is kind of crucial, I think, to getting this correct. So where would you start to solve? Oh, no, don't tell us. We're going to just do it, right? Okay, all right. Just do it there, and then just a Nike slogan, just do it, and then we'll talk about it. There's probably more than one way to approach it, but it's kind of I think kind of a standard way of attacking it too. So again, even if you don't have to get all the way to the end of solving this, okay? Just where would you start? So what is step number 1 there to get this? Huh? Yeah, I can, I think. All right. Yeah.
So
Mm-hmm.
I thought that maybe we could like put x over 3 with negative 1 over 8, like flip them.
Okay. Maybe we can or maybe we can't, but that's not what I would recommend as the first step. Okay. All right. Arthur, what is making what's making this equation yeah. Okay. Yeah, you're on the right track there. All right. Okay. All right. Yeah. Mm-hmm.
Dr. Waller. So
Mm-hmm.
since next negative 3 right here, and I was like, do you multiply every product by 3 or?
You multiply by everything by something, okay? But it's something that would get rid of the fractions. So what number could you multiply everything by that would cause all the fractions to cancel? 3 will not do it. 3 would cause the x over 3 to cancel, but it won't help you with the 12 or the 8. So what could you multiply by to get rid of everything at once? Ah, right, maybe. Okay, so maybe that's the strategy there. Okay.
Well, you don't multiply everything by 24. You multiply what is going to give you 24 on the bottom. So what gives you 24 on the bottom?
Wait. What'd you say, Taylor?
Well, he said you multiply by 24. I was saying you multiply by these. What gives you 24?
No. No. We're not going to add the fractions together. Yeah, we don't care about adding them together. We just care about getting rid of them. So he's correct.
Oh, okay, my bad.
You're going to multiply by 24. Yeah. Okay. Right. Everything by 24 because
that will. You want to get rid of the. Okay,
that's right. I want to get rid of the fractions. Right. Okay. Yeah, you were thinking about adding fractions together. Okay, sorry, I'm going to cut y'all off because I know y'all not to the end of solving that, which is fine, all right? Because again, you can work on it later, or you can look at the and after you worked on it, look at the solutions. All I want to know is where to start, because where to start on this one is really crucial, all right? So let's ask someone where they want to start there. Nadine, what did you do first? You found a common denominator amongst all those fractions, which happen to be what?
24.
But what are you going to do with the 24?
I'm going to multiply it to each number.
Yeah, each term, right, each term. You're going to multiply everything by 24. That is the key there, okay? Because what's the advantage of that, Nadine, multiplying everything by that common denominator of 24? You get rid of the fractions, that's right. So we're going to multiply everything in the equation, the 5x minus 1 over 8, the minus 1/8, and the 2 also. Do not forget the 2, even though there's no fraction there. And then the x over 3, we're going to multiply by 24, okay? Because what will happen is 8 will go into 24, so this 8 will cancel, right? That's a 12, right? I'm sorry, I wrote it down wrong. But 12 will go into 24, so that 12 will cancel. The 8 will go into 24, so this 8 will cancel. Of course, 24 times 2 is just 48, and this 3 will go into the 24 and reduce also, okay? So you end up with an equation that doesn't contain any fractions, and that is what we're aiming for. I think it's this equation, okay? So we still will have an equation to solve, right? And it still may take several steps, but the advantage is no fractions there, right? We've eliminated the fractions, okay? So when you encounter that, an equation like this one, or an inequality with fractions in it, remember, I'd like to get rid of the fractions if possible, okay? And I do that by multiplying by the appropriate quantity, right, times each of the terms in the equation, okay? All right, here's an inequality. So this one, fortunately, does not have any fractions in it, but what are we going to do? Okay, so this is a compound inequality. Remember, compound inequality means you got two inequalities strung together here, all right? So what will be what am I thinking about there if I'm trying to solve that compound inequality? Yeah, 4 less than or equal to 5 minus 3x less than or equal to 11. That's still, let me make it a little bit bigger again. There we go. Okay, I know I'm cutting y'all off really fast, but so I can get to the last couple of problems I want to look at here. So Kevin, where would you start on this one? What was the first thing that you did? So you're writing down really quickly there. What was the first thing that you wrote down? You did what now? To what now? Take away the minus 3. How do I get rid of the minus 3, though? Okay, so Kevin says we want to get rid of this minus 3, which is something we're going to want to do eventually, but you're saying we're doing that by adding minus 3 to what? Yeah, to the middle, and where else here? You have to do it to the left and the right as well, right? Okay, so Kevin's saying let's add 3 to all 3 parts there. All right, Kevin, unfortunately, you've made a kind of a classic algebra mistake there, all right? Because when you add 3 to the middle, the minus 3 is not going away, all right? Because that minus 3 is multiplied by the x. It's not added to the x, okay? So if you add 3 to the middle, it's going to get added to the 5, because those are both constants, and you'll get 8 minus 3x, but the minus 3x is not, the minus 3 is not gone away, all right? So a good try, but just a little bit of faulty logic there, okay? Somebody have a different suggestion of where to start? subtract 5 from all three parts, okay? Then you can get rid of the 5, Kevin, all right? At least get rid of the 5, all right, okay? So that we can do, though, all right? Instead of trying to add 3 there to all three parts, let's subtract 5 from all three parts. All right, or that's the same as adding minus 5 to all three parts. So you would get minus 1 less than or equal to now just minus 3x less than or equal to 6, okay? So we have to do it to all three parts. All right, now Kevin, now you can work on getting rid of the minus 3. But how can you get rid of the minus 3? Not by adding not by adding 3, dividing, right, okay? So because the minus 3 is multiplied by the x, all right? So now we'll divide all three parts by minus 3. And Kevin, when we do that, we have to be careful because we're dividing by a negative, an inequality. So what has to happen to the direction? Yeah, you have to switch it. So these two will become greater than or equal to, all right? Well, y'all can finish the arithmetic there. It's pretty simple, all right? So that is the steps for that compound inequality. Okay, I think we have time for one more. So let me go all the way to the end. The word problem, okay? I know how y'all adore word problems, all right? So let's see where we would start with this word problem, okay? Ooh, we got to go really fast. All right, so Joe Rigatoni has been eating his meals at a square card table, but he must have got a raise because now he has bought a rectangular dining table, all right, to eat at, okay? And it says the new table is 2 feet longer than the old table and 1 foot wider, and the new table has a perimeter, that's distance around the table, of 16 feet. What were the dimensions of the original card table, though? Okay, so how big was the original square card table? Okay, that he was originally eating at before he bought the new rectangular dining table. Okay, all right. So, boy, getting started with word problems. This is something that students always struggle with, but it's such a key part of solving word problems. How would you start that problem? Where would you start on that problem? Okay, so just try thinking about that, right? Where would you start? Just a couple of minutes there. Write something down, okay? There's lots of ways of starting here that would get you to the right answer, I think, okay? So what would you do on the test when you see a word problem? What would you try doing there first? Just take a couple of minutes so we can talk about it before we have to stop here, okay? I'm curious to see what y'all would do first. Okay, we're running out of time, so I've got to stop you. Right, I'm just going to ask you, what was your just sort of initial perceptions of where you would start there, Furman? What would you do first? What did y'all start with? Doesn't sound very definite there on getting started. Okay, I see a time waster coming up on the test. All right. Anybody have a suggestion for the group on where's a place that you might begin, Salma? There, that's what I want to hear, all right? I drew a picture, okay? That's a great place to start here. You can't do this with every word problem because not all word problems lend themselves to pictures, but this one certainly does, right? Because it's got some very simple geometric objects involved. So draw a picture. There are two things you can draw here. The original card table, right, okay? Which is a square, right? And then you've got that new rectangular dining table, right? So I would draw a picture of that first, okay? There's the picture. Now, what are we looking for in the problem? The dimensions of the old table, right, which is a square, right? So the length and the width are the same in the old table. That's what we're looking for. So let's give those dimensions a variable name. We can call that x, right? That's what we don't know. That's what we're looking for. So draw a picture, and then at some point you've got to write down a variable to represent, or variables to represent unknown quantities. So here we go. Let's put x for the sides of that card table. If we know that, then what is this length? X plus 2, perfect, right, okay. And what's this width here? X plus, 1, right, okay. Because this table is 1 foot wider than the old card table. So this is also x plus 1, and this is also x plus 2. See? So we've made progress there. But now we don't have an equation, right? I've got to have an equation involving x. How do I get the equation? What's the one piece of information, Danny, you mentioned it earlier, that we haven't used yet? What? The perimeter. But how do I compute the perimeter of this table? What now? Yeah, so what do I put into an equation? 16 is what? X plus 2 plus x plus 1. No, plus x plus, this is 1, right? Plus x plus 1 again, plus again x plus 2, right? That's don't multiply the two things, that's the area. The perimeter is the distance around, right? I wrote a 2 there mistakenly a moment ago, okay? There's your equation, that's it, okay? Now all you have to do is solve, right, okay? So see, we drew that picture because it lent itself to a picture. We picked variable, right, okay? And then we set up that equation from other information that we had. Then we just solve it. That's easy from that point. All right, okay, so test next time. You know that, right? Do I say that again? Be prepared, okay? I know you can do well. I really mean that, all right?